So in this screencast, I'm going to go through an example to show you how to use Simulink. The example that I'm using comes from Process Dynamics and Control by Seaborg, Edgar, Mellichamp, and Doyle, the third edition. So what I'm going to do is bring up our viewer of our parameters of our system. So we have a transfer function for the system, g of s, and we're going to assume that g of s is the transfer function for the model for the system and as well as for any disturbance changes. So this will apply for set point changes and disturbance changes. And we've already, in the example, calculated several tuning parameters for a PI controller using various different methods for either internal model control with different values for tau c for a desired response, or the ITAE criteria for a first order plus dead time system for two different situations where we are concerned with either disturbance rejection or set point tracking. So, and these are the values for Kc, the proportional gain, and the integral time. And the reason I've included I here will become more obvious when we get into Simulink, but Simulink uses I, the integral time, in a different way in their equation for the PID controller. So I've opened up MATLAB and I've opened up a new Simulink window, and I'm going to click on the library browser to get my blocks that I need to add to my Simulink simulation. So I already have my commonly used blocks. I'm going to look in the continuous blocks and find what I need to represent my transfer function. And what I want to use is a transfer function block, so I'll grab that and put that into my workspace. And I also need a transport delay block. Put that into the workspace as well. And in order to apply control, we need to have a PID controller. So we can also find that in our continuous block. So we'll grab that. And I can make this be a PI controller by just setting the derivative time to 0. So I'll connect these up. And I need to have an input, and I need to have a source, and I need to have a sink. So I'm going to find a source, and the source that I want to use is a step input. So I'll put that over here, and I'm going to use a scope for my sink so that I can see my output. Now, in order to have this be a feedback loop, I need to have an adder put in here so that I can have negative feedback. So I'm going to go into my math operations block and grab an adder block. And here's my sum block. So, but I want to see that I want to add the signal for my set point change, and I want to subtract off the feedback. So I have to change my signs in here and have a negative sign for the feedback that will be coming through. So I can have my step set point change, feed that to my PID, and then I'll grab my signal from the output and feed that back through a negative input or negative feedback. So now I need to define my blocks. First I'll go ahead and define the transfer function block, and basically I want to make it look like what my transfer function looks like. So for the numerator, these are coefficients of s that I'm defining. So for my numerator, it would be 1.54, and the denominator should have a matrix of 5.93, and 1. So 5.93 is the coefficient of the first power of s, and then 1 is the coefficient of the 0th power of s. So that defines my transfer function, and now I need to define my transport delay, and the delay time is just what we have up here, are 1.07. So 1.07. The negative in the exponential means that it's delay. We don't need to put the negative in here because that's implied that that's how that enters in to the simulation. So we just put the theta, or the delay time, in. So we've defined our model, transfer function model, and transport delay, and I'm going to rename this as my system model, and we'll now define what our PID controller should be. So we've already calculated through, we'll do the first one as an example, and through our IMC controller synthesis, we've already calculated what Kc and tau I would be for a PID or a PI controller. And I want to use the ideal form of the PID controller. And actually, since I'm not using any derivative time, I can either set this to 0, or I can go up in my controller here and just select a PI controller. So I'll do that. We'll have a PI controller. So my proportional constant, or tuning parameter, I can see up here in my table I've already calculated that should be 1.27. And then the integral time, if we look at this equation, it enters in as the inverse of what we expect. So when we calculate tau I, we expect that it's in the denominator here with this 1 over s in the form that we've been using in the textbook. But Simulink and MATLAB define it a little differently, so we need to do 1 over tau I and put that in as our I parameter. So we put in 0.169 for I. And now our PID controller, or PI controller, is defined. So we'll click OK. And this is for simulation of a step change in our set point. So we want to take and look at how our step is defined. We really want to have this step time. We want this initial step to happen at time 0. And we want it to be a unit step. So we'll go from an initial value of 0 to a final value of 1. So that is my unit step. So now I'm all set up to run a simulation for a step input, or a step change in a set point. So when I go ahead and run it, I click this play button up here, and I can double click on my scope to open it up and take a look at what my results are. So that looks pretty good. That's what we expect, that it's tracking that set point. Now I want to show you how to simulate a disturbance set point, or a disturbance change, so a unit change in disturbance. So in order to do that, we need to add in a disturbance, and we're going to assume that the transfer function for any disturbance changes is the same as the model for our process. So we're going to just use these same blocks, and I can click on both of them and shift click and copy and paste those blocks and grab them and drag them up here. So I can connect those up, and now I need another summer block. And I'm going to need to move this around a little bit. Instead of doing that, I'm going to just take the signals. This is actually just adding it in. And then I'll move that, send it to the scope, and I want to grab my feedback loop again. So now in order to simulate a step change in disturbance, whoops, I need this to come from over here. I want it to come from after the summer block, after where we add in the disturbance. So I now need to add another step. I'm going to copy this step for an input to get my disturbance. But now I want to have this happen at another time. So let's say at, oops, we'll say at 20 seconds that I want my step and my disturbance to happen. So we'll be able to see both in the same simulation. So I hit play and I take a look at my scope and I don't see the disturbance. Well, the reason is that my simulation time over here I've only defined as 10 seconds. And my disturbance happened after that because I set the disturbance step time to be 20 seconds. So I need to come in here and change my simulation stop time to something like, let's say 40 seconds. So I'll change that and rerun it. And now I can take a look at my scope. And there I can see the set point tracking, and I can also see disturbance rejection. I may even want to run this a little bit longer so I can see how long it takes to really get back to what is the set point. So hopefully this is helpful in understanding how we set up a Simulink model. I can go and do the same thing, changing the tuning parameters to see how the different responses to different tunings and different design methods for our controller would be. But that's the basic idea for creating a Simulink model with feedback in a control system or a control loop and including a disturbance.